So hi, welcome back to my 7th episode of Æther Physics. Today I wanted to talk about the basics of the ether, maybe a little bit more about the history of the ether and why physicists denied, or it's not really denied, but why they forgot about the ether. The story starts, well, way back in time, of course. Physicists did believe there was an ether until 1900s, something like that, because that's when they got confused. In the 1700s, physicists figured out the mathematical rules of motion in a fluid. And later on in time, they figured out the laws of electricity and magnetism and the mathematics of it. And the reason why physicists believed there was an ether was because of the fact that electricity looks a lot like a fluid, especially when you conduct it through a copper wire and you try to do magnetic experiments in the surrounding area close to it. It really looks like as if there is a fluid going through the wire that is rotating like a vortex. And why did they abandon this idea? They abandoned this idea because of the fact that over long distances, the rules of these vortices don't apply anymore. So what this means is that if you would do electromagnetic experiments over a long distance, for instance with radio waves, the calculations wouldn't fit anymore. So they got confused by this because they had a time difference in collecting the data. So the idea that they had was try to measure the movement of the Earth compared to the ether, which was standing still according to physicists. And they couldn't measure it. It didn't matter which side of the Earth you would try and do this experiment, because the Earth is rotating, that's the thing we know. So when something's rotating, it had a velocity on one side and a negative velocity on the other side. So if you would do experiments, you would expect different results, but they always get the same result. They always got the same speed of light. And that's when physicists couldn't figure out why that was happening. And they still can't figure it out today. The only thing they do is express the things we named. For instance, we named a molecule a molecule. We named a body a body. We named mass mass. And these are all terms made by humankind. And these are not nature terms. It's just we do an experiment, we expect something, and we see it happening. With the laws of thermodynamics, the laws of moving bodies and the energy inside the body and the entropy of the bodies, they didn't think of this relative space-time. They didn't think of vacuum as being filled with something. They just saw molecules in empty space. But that empty space wasn't really empty. And some physicists knew, some physicists didn't know. And a fun part of that history is that in the late 1800s, so in Maxwell's time, in the time of Lord Kelvin, before Einstein, Planck's beginning time, Boltzmann's time, it was a different time than we have now. They didn't all believe in the ether. Physicists were separated. We had two different ways of thinking of physics. We had the British way of thinking, which was there is an ether, electricity is ether in motion, and at the same time we had the German way of thinking and the French way of thinking, and they were mostly thinking of energy, of work, of particles that have a statistic way of moving. So the laws of entropy, for instance, these laws are really complicated to understand, but once you understand, it feels like a natural thing. Thermodynamics thinks of space as a 3D place, and this 3D place is filled with small molecules that can have their own velocity factors that move in different directions. So if you contain these particles in a box, so now we had a 3DX and now we're making a box of it, and you say we keep these molecules in this empty box and we have 3 molecules, then for instance the temperature in that box would increase if you decrease its volume. So whenever you give less space for these molecules move more and there is more energy, so there is a higher temperature. So the temperature is about the pressure and the volume of, for instance, a gas or a liquid. And temperature increases when the pressure is increased. Rudolf Clausius. Whenever I heard entropy, I heard Boltzmann a lot. Before Boltzmann, there was Clausius. And Clausius is the one that in papers taught me the idea of temperature for a gas or for a liquid. And Clausius had some really interesting facts in his paper, in his book, I can say, because it's a huge book. The Mechanical Theory of Heat, it's called. You can download it in my Google Drive. As you can see, I have a lot of papers, but the first memoir. It begins in his book with this law, and I think this law is very interesting. Pressure and volume is equal to a constant times another constant plus T for temperature. So it's not a hard mathematical equation. It also says that this R, the constant R, depends on the gas or fluid that you're using. P would be pressure and V would be volume, T would be temperature, R is a constant that is dependent on the change of the body, the change of the fluid. So it depends on, again, pressure, volume and temperature. And there is a constant that was found, I'm not sure if it was Renault that found it. The value of 1 divided by A for atmospheric air is found by the experiments both of Magnus and Renault to be 0.003665. That's an interesting fact that we need to write down, because if you know quantum mechanics a little bit, and you know of the mathematics of quantum mechanics and the constants in quantum mechanics, you would recognize this number. And why? Because in quantum mechanics, we do have the fine structure constant. Usually physicists write it down as alpha. And it equals a number, which is 0.00729. Maybe you already see what is happening here. So the Copenhagen interpretation of quantum mechanics was finished, I guess, in the 30s. It was 1927 that most physicists actually started to believe that quantum mechanics were the new rules of the nature, the basic rules of nature. But in quantum mechanics, you have a fine structure constant that comes back in equations. And the fine structure constant, as you can see, is twice this constant measured by Renault in the 1800s. I just wanted to share that with you guys. I think this is enough for today, and thanks a lot for watching. I would really appreciate it if you would comment on this idea and tell me what you think that's actually going on in the laws of thermodynamics, quantum mechanics, and ether physics. So yeah, thanks a lot for watching. See you next time.